assumption, it's englobe two things that I will tell you about in this part. The process of obtaining the MPK equation begins by making an harmonic analysis of a macroscopical wire. So we have a macroscopical wire of length L. We enlarge it by a little bit, delta L, but still macroscopical. And if we want to obtain the full distribution of this M matrix, we perform a convolution. So this convolution is done in the sense of the group. So this is the M, because these M's, this transfer matrix, belongs to a group. This DM is known as the Hart measure in this group. And here we have the density function of this large system and the little bit extra. So this uniform distribution phases assumption is englobed in two things. Assuming that this probability distribution maximizes the entropy with this thing here. What is the meaning of this thing here? Well, actually, it says that we recover Ohm's law for this little part. So this lambda is the resistance, the average resistance. It's proportional to the length of the system. And this LMFP is something that is called mean free path. So everything that is on here only depends on one single parameter, the mean free path of the system. So with this in mind, yeah.
So what is lambda exactly?
Lambda here is the resistance. The average, well, here is the average resistance.
So, okay. Not the logarithm.
No,
just the resistance.
Just the resistance, yeah. So with that in mind, I'm performing the maximization of the entropy. We obtain this differential equation for the probability distribution, well, the density function of the distribution of this lambda. This lambda is the resistance, the observable, the resistance. We define this lambda because in a sense that we want the probability distribution of the transmission. In a more beautiful way, it's expressed the MPK in terms of this lambda. So the universal parameter that is imposed in this part is this S that actually defines as the average of minus the logarithm of the transmission probability. And here we have a simulation. The simulation is obtained by taking a system of Dirac delta potentials, and we increment the size of the system. This is the n deltas. And solving this differential equation, we obtain the red curve. So this is the classical result and the state of the art. And why is called universal distribution, the solution of that differential equation? Because if we perform a change of variables and obtain the probability instead of lambda, of the logarithm of t, we can see, well, this is extract of a book of Peter Marcos. We can see that it doesn't matter how much disorder we have in the system. The only parameter that defines this distribution is the average of the logarithm of t. Here we have three different systems with three different disorder. W here measures the disorder, 1.5, type 2. And tweaking this disorder and the number of scatters, we recover the same distribution. That's why it's called the universal distribution. But now in our work, we see more or less a paradox, or well, a little problem, if one wants to say, that the requirement of uniform distributions of the phases it's kind of poorly justified for a general disorder system. If we have a system that is periodically, but it have the disorder in the strength of the potential, well, this uniform of the phases doesn't hold up. And it's more peculiar that if we want to study these transfer matrices that belongs to a group, this is in the sense that all the components of this transfer matrix have certain parameters. Well, the group that belongs to the transfer matrix belongs to the group that has 3 dimensions. So at least we have like an intuition that a single parameter scaling doesn't cover the full picture. We have at least 3 dimensions of this is like parameterization of a general transfer matrix. It has 3 parameters. So we have the intuitions that we have more parameters to make the full description of the scaling problem. So the idea is that we are going to do more or less the same that the MPK do. We want to perform an harmonic analysis, make a convolution, and obtain a full distribution. But now we are not going to do in a macroscopical way. We are going to do in a microscopical for a particular system, a system composed for Dirac delta potentials. But we want to recover the macroscopical limit. We want to make this number of delta potentials tends towards infinity. So in these ideas, we obtain for this system particular 2 macroscopical variables. And later on, we will see that this eta is the universal, no more universal single parameter, and it's proportional to it. So we will see later. So the main idea is perform a random walk in the group. This transfer matrix belongs to a group that is called SU11. And why making this? Because I told in the first slide that this transfer matrix behaves when we have a lot of scatters, behaves multiplicative. So if we have a lot of scatters, the transfer matrix of the whole system is simply the multiplication. So it's more or less like a random walk that we sum the individual steps. So here we have a group, so it's not a sum, it's a multiplication. And then in the assumption that these random matrices are independent and identically distributed, then we want to define a normal distribution on the group, like an infinite divisible distribution. That's the main idea. So this idea was developed by Thomas and Alejandro, and they do something like this, but in a compact group. This group is not compact, so we have nothing like the theorem that guarantees the full orthogonalization of the Hilbert space. So we need to do something else to ensure that these things function in this problem. So the justification of this was done by someone called Vilenkin, and he justified this this normal distribution in the limit. So we do a Fourier transform, so we are not doing a study of the density function. We are working with the characteristic function. So with some algebraic manipulation, we develop an expression for this thing that depends on a drift vector, a diffusion matrix, and the generators of the unitary reducible representation of this group. So we obtain a result. I skip the tedious part, so you cannot get bored. And I present the classical result for the MPK. This, well, it can be tweaked out to a more beautiful expression, but essentially, this is the solution to the differential equation. And here we have this exponential decayment. And with our general results, instead of this, we have the Fourier transform in the group. Here, this exponential is a matrix, but for the distribution that we are interested only in the distribution of the transmission probability, we are only taking the central element. It's a matrix of n in the diagonal. Well, 2n plus 1 elements in the diagonal, and we're taking the central element of that matrix. And we can see that in the limit, this limit, when this macroscopical variable tends to infinity, we recover the DMPK solution. And that universal parameter is nothing more than proportional to or other macroscopical variable. So in this scenario, the other limit is also interesting, because if we perform the limit when this macroscopical variable phi tends to 0, we recover a fully periodic delta potential system. So we have the two faces of the same problem. And I want to present a little more results. First of all, in this graph, I plot two kinds of results of two kinds of curves. The continuous of solid lines are essentially exact results. Well, numerically expressions for these exact results, because I program the integral and I perform the integral numerically. And the dashed lines are these matrix, well, the component 0, 0 of this matrix. When I truncate this matrix, because this matrix is infinite dimensional, but I truncate it at some point, and I perform simply numerical exponentiation. And you can see that they are very well fit. So this, well, maybe I need to explain a little bit more, but this P hat is essentially the Fourier transform in this group. Why I do this part of the work? Because we can see that this green curve is, well, you cannot see it here, but I already show you, is the exponential decay. It's e to the minus rho squared. And this pink curve have also an analytical result, but it's super complex, but it can be done in this way. So I can obtain a full distribution that depends on two macroscopical variables, not a single one. Here is the DMPK case. Remember, this phi tends to infinity to recover the MPK, but we see that in the extent of the work, we see that it's only, or infinity, it's 10. So it's kind of fun. So here we fixed this phi for the MPK case, and we only change the eta macroscopical variable. So for 2 and for 8. These results are already known. Actually, if you integrate the differential equation by any means of numerical solutions, you can obtain this red curve. But here, the important part is that it's a limiting process of our calculations. And now we study an intermediate case. Now this phi, remember the two limiting is infinity and 0. Well, we are in something in between. It's an intermediate case, and we also developing evolution of this eta variable. So again, it fits the simulations. That this blue histogram is the simulations. And this is the extreme cases. The extreme cases, periodical system. This phi tends to 0. Here is more near 0. And we evolved this eta variable. Now you can see that this eta doesn't start at near 0. It's start much bigger. And here with 15 and 20. Everything already noticed that in some of the plots, we have some path behavior of or result, analytical result. And we are working already in this, but the meaning of this path behavior is because in the integral, we have a cone function that behaves oscillatory. That's the meaning of this path behavior. And we are already attacking this problem by making asymptotic approximations. But the main part of this part, well, the central part, is that this oscillatory behavior doesn't affect the convergence of the probability distribution. We already proved that our expression of the fully probability density function converge for all eta and all phi. So it's a problem, a numerical problem. And now, for the end of this talk, I show you a change from the ballistic to insulation regime. So what is ballistic regime? When the probability of transmission between these system tends to 1, and when probability of transmission tends to 0, well, we are in the insulation regime. So if we expect this simulation was done before the other graphics, but I want to present here to make a conclusion. If we expect that a single parameter is universal, we expect that such parameter, for some observables, we have the expected value of 1/t. It's a single curve. And it happens to be in the ballistic regime, ballistic versus insulation regime. But actually, in the insulation, it's not anymore. So what is telling us this plot is that we are in the good path. So we are working in finding a fully complete probability density, or well, probability distribution for a general one-dimensional system. Here we have two macroscopical variables, but the prospects to continue this research is to implement alternative distributions for the delta parameters, where, well, I didn't say, but the parameters of the delta are the strength of these deltas and the distance relative between neighbor deltas. And the other thing is design a model, a system that allows a third macroscopical variable. I already told you that SU11 is a three-dimensional Lie group. So for the general picture, we need a third macroscopical variable. We have an idea of this, but we are not working already in that part, but we have an idea on how to obtain this third macroscopical variable. And well, this is a work that's it's like more or less stop right now, but we want to perform an analogous study of this probability density function, this general probability density function, but when we have drift. When I present you the Fourier transform, I told you that it depends on a drift vector and a diffusion matrix. Well, it's kind of good for us that when we study the deltas, we have no diffusion. So we want to study when diffusion occurs. And finally, extend the validity.
You said it wrong, right? You have no drift.
Oh, yeah. Sorry, we have no drift, but we want a system that has drift. And finally, extend everything that is done here to quasi one-dimensional system, because the MPK, essentially, the robust part of that theory, belongs to quasi one-dimensional systems. So that's some reference. Thank you.
Another question?
Yo creo que aquí, pues, originalmente la ecuación de MPK te parece un 2, ¿no? ¿Te parece un 2 o para qué?
No, es
Uno. Y usted le quiere hacer ese 1, ¿no?
pregunta. Nada más para aclarar, tal vez, hablaste de que en general uno espera, uno tiene una matriz de difusión y un vector de drift.
Sí.
Entonces, ¿cuántos parámetros podrías tener al final?
Entonces, sí, esencialmente los 3 del drift y los 9 de la matriz de difusión. Y estas componentes de estos, ¿no?
Es que la matriz de difusión tiene unas... tiene que ser
Bueno,
simétrica.
ya, sí.
Son 9.
Ajá, 6 y 3. 6 y 3. Sí, solo que todas estas componentes pues deberían depender de las variables macroscópicas.
Sí, o sea, todos son variables potencialmente.
Potencialmente, sí.
Muy bien.
Gracias.